Welcome to section 9.1, a statistical test of hypothesis. In this section, we dive into one of the most important tools in statistics, hypothesis testing. You'll learn how to make data-driven decisions using the logic of evidence to support or reject a claim. Whether you're evaluating whether a new teaching method is better or whether an in-game item drop rate in a popular video game matches the developer's claim, hypothesis testing is your method of choice. Today, we'll focus on tests about population means and proportions when sample sizes are large. A hypothesis test is a formal process used to evaluate whether the data supports a specific claim about a population. We start with a claim, gather data through a sample, and then use statistical logic to determine whether the data supports or contradicts the original claim. Think of it like this. Suppose a university claims that students spend at least 3 hours per day studying. You might question this and collect data from your peers. If your findings suggest otherwise, a hypothesis test helps you determine whether the evidence is strong enough to challenge the university's claim. We begin every test with two opposing hypotheses. The null hypothesis, H with the subscript of 0, represents the status quo or no change. It's the claim we initially assume to be true. It's like the statistical version of innocent until proven guilty. It represents the status quo, no effect, no difference, no change. The alternative hypothesis, which is usually written with an H with a subscript of 1 or an H with a subscript of A. The alternative hypothesis is what we hope to support, the statement that suggests a change or difference. It is the claim we're investigating. It reflects the idea that something has changed or that there's a difference from the expected. For example, if a coffee shop claims their average wait time is 5 minutes, you might test the null hypothesis that the population mean is 5 minutes against the alternative hypothesis that the population mean is greater than 5 minutes if you suspect they're slower. Let's look at another relatable example from gaming. Suppose you believe that Fortnite players are gaming more than usual. The game developers claim the average weekly play time is, say, 8 hours. So our hypothesis would be our null hypothesis, H sub 0, would be that the average is equal to 8 hours. So mu equals 8 hours. And the alternative would be the average is not 8 hours. So mu does not equal 8 hours. This setup, using that not equal to, is what we call a two-tailed test because we're looking for evidence that the average is either higher or lower than 8 hours, not just one direction like we had with the coffee shop up here. We might be checking if players are grinding harder due to a tournament or maybe playing less during exam week. Either way, the alternative hypothesis lets us explore those possibilities. Choosing the right alternative hypothesis depends on the question you're asking. Is it a difference, an increase, or a decrease? As we just discussed, we only care about results in one direction in some tests. That's a one-tailed test. For example, are players spending more time in Apex Legends since the new update? Other times, we're open to detecting changes in either direction. Those are the two-tailed tests. For instance, has the average screen time changed this semester? Maybe it increased or maybe it decreased. The type of test affects how we calculate the p-value. In one-tailed tests, we only consider one end of the distribution. In two-tailed tests, we consider both. Once we've set up our hypotheses, we compute a test statistic which tells us how far our sample result is from what the null hypothesis predicts in standard error units. For larger samples, we use the z statistic. The z equals x bar minus mu naught, the population mean, over sigma, the population standard deviation, divided by the square root of n. Or, for proportions, p hat minus the population proportion, p naught, divided by the square root of p naught times q naught. Remember, q naught's 1 minus p naught over n. Think of this like measuring how many standard errors away your sample result is. It's like saying, I'm 2 standard deviations taller than the average person, except now we're measuring how unusual a sample statistic is. The p-value is the probability of getting a result as extreme or more extreme than your sample result, assuming that the null hypothesis is true. A small p-value, typically less than 0.05, means your result is unlikely under the null hypothesis, which gives you evidence to reject the null hypothesis. Let's say you're testing if players in Fortnite land more headshots than usual. If the usual headshot rate is 20% and your sample of players has a rate of 28%, your p-value tells you whether that jump is statistically significant, or could it have just happened by chance? Here's the step-by-step procedure for hypothesis testing. First, state the hypotheses, the null and alternative. Second, check your conditions. Is the sample size large enough? Is the data random? Third, compute the test statistic z using the formula we just discussed. Then 4, find the p-value based on z using either technology or a table in the back of the book. Fifth, make a decision, compare p to alpha, and decide to reject or fail to reject the null hypothesis. And then 6, state the conclusion in context. Always tie your conclusion back to the real-world question. This structure is universal, whether you're testing a new medicine, a marketing strategy, or a game mechanic update. Now let's talk about the language on step 5 there. When we conduct a hypothesis test, we're trying to determine whether the evidence from our sample is strong enough to go against the null hypothesis. That's our default assumption, like the status quo. Now you might wonder, why don't we ever say we accept the null hypothesis when we don't find enough evidence to reject it? That's a great question, especially since your textbook gets it wrong and says accepts the null hypothesis. But we don't do that. We say fail to reject. The answer lies in how statistics works. Why we say fail to reject instead of accept is because we're basing our decision on a sample, not the entire population. And samples carry uncertainty. Just because our sample doesn't provide enough evidence doesn't mean the null hypothesis is true. It simply means we don't have enough data to prove otherwise. Let's use a courtroom analogy. Something you may be familiar with from shows like Law and Order or She-Hulk, Attorney at Law. In court, the default assumption is that a person is innocent, like the null hypothesis. The jury doesn't have to prove innocence. They just need to decide whether there's enough evidence to declare guilt. If there's not enough evidence, the verdict is not guilty, not innocent, because we can't prove innocence. We're just saying the evidence wasn't strong enough to reject that assumption. That's exactly how a hypothesis test works. So instead of saying we accept the null, which sounds like we've proven it true, we say we fail to reject it. This keeps the door open. With more data or a different study, we might reach a different conclusion. Let's walk through a full hypothesis test using a scenario that might sound familiar to the gamers among you. Imagine a new DLC, downloadable content, is released for Elden Ring. The developers claim that the expansion increases the average weekly playtime of users from 6 hours to 7 hours. As statisticians, we want to test whether this claim holds up with real data. All right, step one, state the hypotheses. We always start by setting up our hypotheses. The null hypothesis is that nothing has changed, so the average time is still 6 hours. The alternative hypothesis is that the average time has gone up, so we're testing if mu is bigger than 6. Since the developers are claiming an increase, this is a right-tailed test. We're only interested in whether the average has gone above 6, not if it's different in any direction. So when we're looking at a normal curve, we're only interested in the right side, the bigger than. All right, step 2, we're going to compute the Z statistic. We collected a sample of 64 players, and their average play time was 7.3 hours. We're told that the population standard deviation, sigma, is 1.2 hours. Let's plug that into the Z formula for a population mean. So we get Z equals our sample, 7.3, minus the population, right, 6, divided by the population standard deviation, 1.2, divided by the square root of our sample size, that's 64. So we get about 8.67. A z-score of 8.67 is way off in the right tail of the normal curve, like boss level extreme. So over here, our 8.67 would be way out in the right field, right? Remember, z-scores are the mean is centered at 0. So we're clearly in that rejection region. So now step 3, we would interpret the results. A z this large means the corresponding p-value is nearly 0. That's far smaller than any typical significance level like 0.05. In other words, this outcome would be incredibly unlikely if the true average was still 6 hours. So we reject the null hypothesis. Our conclusion? There is strong statistical evidence that the DLC increases average playtime. The developer's claim holds up. Players really are spending more time exploring the lands between. Now let's talk about a critical concept in hypothesis testing, the significance level, which we symbolize using the Greek letter alpha. So what is alpha? It represents the probability of making a type 1 error, that is, rejecting the null hypothesis when it's actually true. In plain terms, you're saying something has changed when it actually hasn't. It's like raising an alarm for an intruder, but it turns out that it was just your cat knocking over a lamp again. Common values for alpha are 0.05 or 0.01, depending on how cautious you want to be. An alpha of 0.05 means you're willing to accept a 5% chance of falsely rejecting the null, a pretty standard level in most scientific research and business testing. Now, this brings us to the rejection region. Think of it as the danger zone on our bell curve. If your test statistic falls in that region, you reject the null hypothesis. In a right-tailed test, lost my pen there we go. In a right-tailed test, that rejection region is on the far right end of the distribution. Maybe you're testing if playtime increased after a fortnight update. In a left-tailed test, it's on the far left. Say you're testing if customer satisfaction dropped after a policy changed. Now, in a two-tailed test, the rejection zones are at both ends, like testing if average hours played changed, whether it went up or down. Imagine it like a boss fight in a game. You only lose health, reject the null, if your actions land you in that high damage zone. the rejection region. And the size of that zone depends on your alpha. A smaller alpha means a narrower rejection region, so you're being more conservative, only rejecting the null in more extreme cases. This is why choosing your significance level is a big decision. It's your balance between caution and risk. All right, a media company claims that 60% of Gen Z college students prefer Disney Plus over Netflix. You're a bit skeptical, so you conduct your own survey. You ask 100 students, and 52 of them say they prefer Disney Plus. So our question is there enough evidence to reject the company's 60% claim? We'll test this using a significance level alpha of 0.05. Go ahead and pause the video here and try to solve the problem. Hit resume when you're ready to check your solution. All right, step 1, we're going to set up the hypotheses. We want to test the company's claim, so we define our hypotheses like this. The null hypothesis is that the proportion is 0.60. This means the true proportion of Disney Plus fans is 60%. And our alternative hypothesis is that it's not, does not equal. So P does not equal 0.60. This means the actual proportion is different, could be higher or lower. So it's a two-tailed test. From our sample, the sample size N is 100. Sample proportion P is 52 out of 100, so 0.52. And the claimed population proportion P naught is 0.60. All right, so then step 3 is to calculate the test statistic Z. We'll use the formula for Z-score for a sample proportion. So it's our P hat minus P divided by P times Q. Remember, Q is 1 minus P, so 1 minus 0.6 is where that 0.40 is coming from, over N, all under the square root. We get about negative 1.63. Look up the probability using technology or the chart in the back of the book, and you see P is about 0.1036. So because this is a two-tailed test now, we find the area in both tails. Here's our 0 at the mean. Beyond 1.63 and negative 1.63. That shaded area is this P equals 0.1036. Now, the way that we look it up, if we're using a Z-table or technology, either way, right, we would find just the area on one side, which is going to end up being about 0.0518 if you look it up in the table. But because we know this is a two-tailed test, we multiply that by 2 to get the area over here as well and get that total 0.1036. Now, by the way, don't confuse this P for probability with the P for the population proportion. All right, step 5 is to compare the p-value to alpha and make a decision. We're using alpha equals 0.05. Our p-value is 0.1036, which is greater than 0.05. So we fail to reject the null hypothesis. Step 6, interpret the result. There is not enough statistical evidence to say that the proportion of Gen Z students who prefer Disney Plus is different from 60%. Even though your sample showed 52%, the difference isn't large enough to be statistically significant at the 5% level, meaning it could easily be due to random sampling variability. Large sample z-tests are appropriate when your sample is large enough for the central limit theorem to kick in. For proportions, this usually means both NP and in Q, or remember Q is 1 minus P, both in P and in Q are at least 10. For means, the sample size should generally be at least 30 unless the population is known to be normally distributed. If the sample is too small, we'll need to use a different method, like a t-test, which we'll explore in a later chapter. Let's bring it all together and walk through the core logic of hypothesis testing step by step. Start by assuming the null hypothesis is true. This might seem strange at first. Why assume something you're testing? But that's how the process works. We take the null hypothesis as the status quo, the default, and only challenge it if we find strong enough evidence. Next, we measure how extreme our sample result is under that assumption. Basically, we ask, if the null hypothesis were really true, would a result like this be likely? If your sample result is something you'd rarely see by chance, then that's a big clue that something might actually be different. Then we decide whether the evidence is strong enough to reject the null hypothesis in favor of the alternative hypothesis. If our result is in the rejection region, or the p-value is less than alpha, we say, okay, this is too unlikely under the null hypothesis, so let's reject it. Let me give you a real-world analogy. Imagine you're on a debate team. The opposing side, let's say the null hypothesis, starts with the benefit of the doubt. They don't have to prove anything. It's your job, representing the alternative hypothesis, to bring in solid evidence and make a compelling case. If your argument is weak, the judge won't overturn the status quo. But if you bring strong, clear points, evidence, data, and logic, you'll win the round. It's the same thing with statistics. That's the rhythm of hypothesis testing. Start with the default, test your evidence, decide if it's strong enough to convince the judge, the data.